Okay, good morning everyone. We have two topics we can discuss today, and it doesn't bother me which topic we discuss. We can either do naming of aromatics or reactions. And I'm kind of leaning towards doing reactions, give you the weekend to think about it, and give you a little bit more time to study it, and then that can be Monday's topic along with some miscellaneous stuff for the naming of the aromatics. And then that'll kind of bring us to a draw for the end of that chapter. And so I'm looking at potentially a test next week Friday, or it would be like the following Monday or Tuesday. Although, again, we're going to play it by ear. We'll see how things go, how well people are doing on things. Okay, so let's take a look at reactions in chapter 20. So reactions of molecules that have a carbon-carbon double bond or a carbon-carbon triple bond. And so we need to review a new mechanism. It's called an addition reaction. And an addition reaction makes use of the idea that the electrons in a carbon-carbon double bond or the carbon-carbon triple bond, and we're specifically talking about those pi electrons, are very exposed. Therefore highly reactive. And we saw that, for instance, if we took an alkane plus bromine, that reacted very slowly, and that we almost needed UV light to get it to go fast. But when we did that reaction with an alkene, that happened very quickly. And so the reactions that happen between alkanes and alkenes both occur. It's just mostly a question of how quickly they occur. Most alkane reactions take a long time to happen because those carbon-hydrogen bonds are pretty stable. They don't break all that easily. Whereas we'll find that the carbon-carbon double bond and that carbon-carbon triple bond break much, much easier in this. So an addition reaction, another name for it from like last chapter, or last year I should say, is really what we're looking at is a combination reaction. We're going to be taking two reactants and we're going to make one product. Now I'm going to put a star there because generally there's more than one formed, but one is highly favored. So it's kind of like reactions with alkanes. There's multiple products involved, although with carbon-carbon double bond and triple bond reactions, there's only usually two products. And one product is usually highly favored, sometimes as much as, say, 100% to 0%, but it can vary a bit. And so what we'll do is we'll practice drawing both products, and again, we'll circle the product that is most favored in those reactions. I should also point out that for every reaction with a carbon-carbon double bond, there is a corresponding or the same reaction basically with a triple bond. So what you'll find is that most of my examples will probably be with carbon-carbon double bonds, just because they're a little easier to see what's happening. It's a little easier to just focus in on the one step. And then realize that for every reaction I show you with a double bond, we can also do that reaction with a triple bond for this. You guys with me so far? Okay, I will remember to not hit the keyboard in frustration.
I had my headphones plugged in, and it was like a pretty loud mouth, and it hit, and then it stopped. Oh God.
Sorry, we will make sure we don't do that. That was totally off topic, sort of. Okay, so the first reactions that we're going to look at are those addition reactions, and if I'm thinking about it in words, what I'm really saying is that I can take an alkene plus a variety of different compounds, for instance, a halogen, and make an alkyl halide. Or I can also react it, we're going to find, with hydrogen gas, water, and HX, which are acids. And they all make and do the exact same thing. And so what you really have is one reaction mechanism with 4 different possibilities as to what's being reacted. Oh, like this? Wait, where's there a space?
She's saying there's supposed to be a space between alkyl and halide.
Oh, no, it's one word.
It's one word.
Actually, for all I know, it's 2 words. I don't really know off the top of my head.
So it doesn't really matter if you do one.
No. And we sometimes call those halo alkanes as an alternate name, meaning it's an alkane with a halogen stuck on it. And the way carbon-carbon double bond reactions work is we break that carbon-carbon double bond. So if I take a look at the most generic possible way that I can write this reaction, there's a carbon-carbon double bond, right? Plus my halogen. And remember, X2 can be any type of compound. And the first step is we're going to break each of those bonds. And then I usually like to show the molecules lined up. And so what's happening is I'm breaking that bond, and each one of the carbons gets one of the electrons from that pi bond. And at the same time, I'm also going to break that halogen, and then each of those halogens is going to have one lone electron. And then I guess we can show the other pairs of electrons just for completeness sakes. And what really happens, if we're kind of trying to have a mental image, is that the halogen approaches the carbon-carbon double bond pi electrons. And remember, those are exposed, and is more attracted to those electrons than the ones in the current bond, meaning the current X2 bond. And what it's really saying is that halogens are greedy. They're going to take the electron that they can have the most. And the way that they can have an electron the most is if they form a bond with carbon, meaning it's easier to steal an electron from carbon than it is to steal an electron from another halogen. That might be another way to say it. It's easier to share, I shouldn't say steal, share an electron with carbon than another another halogen because of the electronegativity. Meaning, remember, in a shared bond, halogens really want those shared electrons, but carbon doesn't really care so much about the shared electrons in a bond, and it's more willing to give it up. And so the halogen would rather share a bond with carbon than with a halogen. So if we kind of continue this, and you can draw it off to the side, up, down, however you want, what we end up with is forming a new bond between each of the carbons and one of the halogen atoms. And so we've really basically added 2 atoms, one on either side of the carbon-carbon double bond. So all we're really doing is adding something on either end of the carbon-carbon double bond and turning it into a carbon-carbon single bond. This is, I don't know, I guess my theory on these first sets of reactions is they're all very easy. The worst part about it is they're all very similar. So it's easy to get confused which one is which. And I do have to admit, the ones that have lots of multiple products, that can be a little tricky, definitely at first too. But the mechanisms are pretty easy. Substitution, elimination, and addition are pretty straightforward. So if we drew that in a line drawing, what we could say is that, here's my carbon-carbon double bond plus, say, a chlorine molecule. And the way I like to illustrate it is I just draw an arrow and say, well, that one chlorine's going there and one chlorine's going to the other end. And we just get a molecule that has two chlorines stuck on it. Jasmine, do you have a question? I can go back a page if you want. I mean, if that makes it easier. So real quick quiz. If I have an alkane as my reactant, what are the only two possible mechanisms? What? Louder. Elimination and substitution. And if I have a carbon-carbon double bond, the only choice that we're going to have is addition. And we're going to talk about one other type of reaction too. And I guess, if I'm really being broad and general, we can always combust everything. It doesn't matter. It's the same reaction for all types of compounds. So the nice thing about this is it doesn't matter how ugly I make my chain. If I draw a bunch of side chains on it, and I can even have side chains on side chains, I can get as creative as I want. What's the only part of that molecule that matters? Yeah, this is the only part that matters. The hard part in this reaction might simply be drawing that ugly-ass molecule and making sure that you copy down all the crap that I stuck on it. And certainly we can't even name this molecule because we haven't really talked about how to do side chains on side chains. So we're not even going to do that as an exercise. So when you see a carbon-carbon double bond in a reaction, just think, I'm going to break that bond and I'm going to add something to both sides. Now it does get a little bit more complicated than that, because what I added here, notice that this is symmetrical. Meaning, chlorine, chlorine is just two chlorines. If I add something unsymmetrical, that's where we can get more than one product. So for instance, if I take this reaction plus HCl, I actually get two products because I've got two choices. Meaning the hydrogen can go on this end or the hydrogen can go on this end. And if we do that, then that simply means that the chlorine can also go on one of the ends or the chlorine has to go on the other end. And so we really get two products. We get one where the hydrogen is in the middle and the chlorine is on the end. And we also get one product where chlorine is in the middle and hydrogen is on the end. Remember, the double bond always breaks. So anytime we have an alkene, then what we're going to do is we're going to break that carbon-carbon double bond and just be left with an alkane plus some stuff stuck on top of it. Jasmine? Well, we don't have to show it, meaning you don't have to show that that's there. Because we said that in line drawings you can leave off the hydrogen, right? But I'm showing it's there because I'm emphasizing the fact that that hydrogen was added to that molecule, that there wasn't a hydrogen there before, and that that's one of the two possibilities. So it helps me keep track of them. So if you wrote your answer just like this, that's a perfectly acceptable answer too. I like to show just a little bit extra that, I really did add a hydrogen to that molecule. Helps me keep track of things. And then one of those two molecules is favored, and it turns out that this one is about 100% made, and this one is about 0% made. And it's not always 100-0. Sometimes it might be 95-5. And there might be cases where it's even closer to, say, like 60-40 or something. But there's always one that's favored. What? Why is one favored? Well, there's two reasons why. I mean, first off, we can simply take and talk about Markovnikov's rule. Don't quote me on that spelling unless I go look it up in my, Markovnikov. Yeah, Markovnikov's rule. And so I'm going to tell you the rule, and then I'll tell you the reasoning behind the rule, and hopefully that'll answer your question. If not, ask the question again, and we'll re-examine it. And what Markovnikov's rule says is that the hydrogen goes to the carbon with the greater number of carbons or hydrogens. Yeah, so this is good, someone's paying attention. This is basically the opposite of Zaitsev. So one of the things is, and I got to be honest, every year I have to refresh my brain on this because I can never remember which one is it goes to the greater and which one is it goes to the lesser. And so Zaitsev's and Markovnikov's rule are very easy to get mixed up. Another way to phrase that is simply the non-hydrogen, meaning whatever else is there, goes to the carbon with the least hydrogens. Which is saying the opposite. If the hydrogen goes to the carbon with the most hydrogens, then obviously whatever else is being added has to go to the carbon with the fewest ones. And the reasoning behind that is much the same as the reasoning behind Zaitsev's rule. And the reason why the rules are kind of opposites is, remember, in Zaitsev's rule, we're eliminating something, right? We're removing it from the molecule. Whereas in Markovnikov's rule, we're adding it to the molecule. And so removing and adding are kind of opposite processes, right? Wait a second, did I circle the wrong one? Oh, I'm sorry, I did mix it. Ooh, that's horrible, Jay. You know why? Is because when I look, I wrote the products back. I was gonna say I wrote the products backwards on the board from what my notes are. So when I looked down to my notes to circle one of them, I glanced at and circled the wrong one. So yes, the hydrogen goes to the carbon with the greatest number of hydrogens. I apologize. I am glad someone's paying attention. Was that Brittany again?
The other one has more hydrogen, but then maybe I'm wrong. I don't want to say anything.
Gotcha. So yes, if we look, there's two hydrogens here, and there's only one hydrogen there to start with. And so we would, do it that way. Yes, thank you for keeping me honest on this, because I got to be honest, sometimes when I'm lecturing, I don't actually think what I do. I look down my notes, and it's like, oh, look, I circled the top one in my notes. But then I should have paid attention and noticed that I also drew them backwards. And so the reasoning behind this is that idea of carbocation stability. And if you guys remember when we were doing Zaitsev's rule, we basically said that the least stable one is if I have something like this, and they get more stable as I add more and more R groups to it. Oops, that's a plus sign there. And so this end is the most stable. This end is the least stable. And if you remember, we also called these, because it's easier than writing the structure, primary, secondary, and tertiary carbons.
Where did you circle?
That's supposed to be a little plus sign. Sorry. Usually I circle plus signs, mostly because otherwise they look like other things. So I wasn't doing that very consistently here. And what that really does is that by adding the hydrogen to the carbon with the most hydrogens, it gives you the most substituted carbon. And so it's the least stable, and that's why the chlorine or whatever else reacts with the other one. So let's look at some more examples. And here's the nice thing about these. Once you master these, it doesn't matter what other crap I throw on there. I can throw as much crap and as much side chains as I want on that molecule. And the only thing that matters, oops, I got to add something to it, right? Let's add HBr just to be fun and different. The only thing that matters is that I've got a carbon-carbon double bond. And so maybe I shouldn't have drawn this because now I have to redraw it like twice. Let's see, can J draw this more than once the same way? There's one. Okay, I lied. The hardest part about this reaction is simply drawing the molecule twice the same. There we go. And on one of them, I'm going to have H and Br, and the other one I'm going to have Br and H. Yeah, I picked a horrible example. I don't know why I jumped to something like this. I guess I was trying to prove the point of the reaction itself is really simple, right? Meaning just putting an H and a Br on either end of the double bond. The hardest part about this is just drawing the stinking reaction. Or just, I mean, not drawing the reaction, but drawing the stinking molecule. So which one's favored, top or bottom? Yeah. Hydrogen goes to the carbon with the most hydrogens. This has got one hydrogen. This has no hydrogens in this case.
So you just picked any spots to put those?
Well, notice it's where the double bond was. So the nice, if you see a double bond on the reactant side of a reaction, all you have to do is add stuff on either end of it. That's it. Addition reactions are easy, at least in my mind.
Bagel is not good.
How can a bagel not be good?
It's just bagel.
Now, of course, I'll go back to a simpler example just for fun, or just because. We can, of course, add lots of different things, meaning we showed how to add a halogen, we showed how to add an acid, we can certainly add a water, and in this case, again, we get two products. So I draw two molecules. One of them gets an OH here and an H here. The other one gets an OH and an H. And since I hopefully do this randomly, I don't know which one is the answer, but top or bottom, most stable. See, hydrogen goes to the carbon with the most hydrogen, so the top one again. Was that the last example too? Dang it. I figure by random chance, sooner or later, it should be the bottom one. I've had some people say, oh, it's always the first one you wrote. And I'm like, that was how they did the homework. They just, whichever one they drew first is the most stable. And I'm like, no, if my examples were like that, then I didn't make very good examples necessarily, or you didn't realize that I got a 50-50 chance for it always being the top, right? I figure if I do 5 or 6 examples and it's always the top, that's like flipping a coin 5 times and getting heads. That doesn't usually happen very much. Now, you might recognize this. These are called alcohols when they have an OH on them, and that's going to be the topic of chapter 22. So we're going to see this reaction again in chapter 22 because it's the way we make alcohols. And then the last thing that we can add that's interesting, or maybe not so interesting, take your pick, is hydrogen gas. And since that's symmetrical, there's only one product because whether I add the hydrogens, which hydrogen goes to which side doesn't matter. And so the idea is that if I have something that's symmetrical being added, then that gives me one product. And if I have something that's not symmetrical being added, then I go to 2 products. So most of my answers are going to have 1 or 2 products. The only way we can make it harder is if I put more than one carbon-carbon double bond in the reaction, which, you know, maybe I'll do one of those, but honestly, all it does is mean there's more possibilities, right? Meaning, if I have something like this, plus, say, HCl, then I really have 4 possibilities, right? So I'm going to draw 4 molecules. Because on the first one I can go HCl, and then I can do that the same twice. And then on this end I can go HCl and then swap it and go ClH. And then here I need to go ClH, ClH, and then here I can go again. Oops, Jay's being silly. HCl, HCl, ClH. And so really, that's the only way I can think to make these even remotely fun, is to put lots of double bonds in them. That being said, you'll notice that I doubt there's that many, if at all, any examples like that on the website. But I don't know, if I get time, I'll add them just for fun. So this makes it a little harder. Which one is the most favored? What I would do is break it into 2 steps. If I'm looking at this reaction, which one's the most favored? So notice that this would put the H and the Cl like this, right? And if I'm looking at this one, the most favored would have the Cl and the H like that, right? So I need to go HCl, ClH, HCl, ClH. Good, it's not the top one. I figured this is the only way I could make sure it wasn't the top one. If I put enough possibilities down there, the percent chance that it's the top one is less and less, right? Now we're going to do one with 3, no, just kidding. We're not going to do one with 3 triple bonds, or double bonds. So I said that molecules with triple bonds react the same way. They just react twice as much, meaning that I really need to technically put twice as much chlorine in there, because I can break this side of the triple bond and add a chlorine, and I can break this side of the triple bond and add a chlorine. And so what I'm really doing is the reaction twice, or I'm going from a triple bond to a double bond, and then from a double bond to a single bond. So I'm really adding to both of those sets of pi electrons. And so if I have the same thing being added, then I only get one product. But if I add lots of things to it, or if I add something that's unsymmetrical to it, then I can get multiple products. So for instance, if I'm adding HCl to it, then let's see. The first time I break the double bond, or the bond, I can get an H and a Cl, right? And so that can be like that. And then what differs is I can add the Cl and the H here. And here I can add them on the same sides. And because I picked a really symmetrical molecule, there's only 2 products to this, right? Because even if I switch the way things are, because I picked a nice simple molecule, there's only 2. And is either product favored in this case? No, because again, I picked a nice symmetric, easy molecule, right? Yeah, technically I should put a 2. But even if the 2's not there, we realize that we almost always add. I mean, the bonds are so reactive that basically you just react both of them at the same time. Let's do an unsymmetrical one. See, you guys are doing so good, I'm actually stretching and making this harder than it should be. So let's add water this time. And so I should be able to get a whole bunch of products this time, I think. Let's try it. Because, let's see, I add an H and an OH, and then if that first one is the same way, I can add an H and an OH. And so here I can add an OH, and I can add it the same way, H and OH, and here I can add HO and H. And then if I do them the other way, I should be able to get an H and an H and an OH and an OH and an OH and an H and an OH, OH, and then H's like this. So I should be able to get, oh crap. What, so HOH, HOH. So then this one needs to be OH. No, that's the same too. Did I pick something that's still too symmetrical? Maybe I did.
No, OH, H, OH.
No, that's this one right here. Maybe there is only 3 products. So I can stick both H's on one side, I can stick both H's on the other, or I can swap them. And because when they're swapped, that's the same as if I did it this way, right? And so really there's only 3 in this case. And I don't think in this case either one is going to be favored either. So here we can only get 3. But the idea is that triple bonds do exactly the same as a double bond, but twice as much, meaning you add stuff to both sets of the bonds. Okay, one last reaction for this type, and this is going to be a new type of reaction. We're going to go into it in a lot more detail in future chapters, but this is the first time we kind of see it, and this is called an oxidation reaction. And do you guys remember oxidation and reduction when we discussed them before, just a tiny bit? And I'm trying to remember, it might have been my other chemistry class that we talked about them at all. So in an oxidation reduction reactions, or in an oxidation reaction, it's really paired, meaning you also always have a reduction reaction. And so sometimes these reactions are paired and they're simply called redox reactions. And whether we label something as being an oxidation or we label something as being a reduction simply matters, or simply is which molecule we care about. So if the organic molecule is oxidized, we'll call it an oxidation reduction, even though something else in that reaction has to be reduced, meaning they're paired up. And if the organic molecule that we care about is reduced, we'll simply label it a reduction mechanism. And so there really is 2 parts that are paired. There's oxidation and there's reduction. And the technical definition of them is, let's see, make sure I get this, GER. Leo the lion goes GER. So this one is lose electrons, oxidation. And this is gain electrons as a reduction. And the way I remember that is Leo the lion goes GER. Because I got to be honest, this is one of those 50-50 things in life. You're either gaining or losing electrons. And so it's very easy to get them mixed up. But if I remember Leo the lion goes GER, it's easy. Because if I lose electrons, I know I'm being oxidized. And if I gain electrons, I know I'm being reduced. And so the hardest way, and see this is what's weird, so is to follow the electrons. But this is not always easy. And we usually won't bother following the electrons around in a reaction, although when we do get to some of the biochemistry chapters, we do want to look at where the electrons go. Does Todd cover electron transport chain in Bio 111, I'm assuming? Or is it in Bio 112? Yeah. So you guys have all heard of that. We won't even go into barely talk about it at all, mostly because the reactions are too complicated to even want to talk about. The way we generally recognize oxidation and reduction reactions is if I gain bonds to oxygen, or since this is the opposite, I'm going to lose bonds to oxygen. And here I'm going to, of course, lose bonds to hydrogen, and here I'm going to gain bonds to hydrogen. And so those are the two easiest things to do, because it's very easy to count how many bonds there are to oxygen and how many bonds there are to hydrogen. And that'll get you the answer probably 95% of the time. And 95 is good enough to usually make that our best way. And we'll learn when we do the bioenergetics chapters, and I don't know, has Todd talked about that in Bio 111 or not, where energy storage and things like that in biology? Does that ring a bell? We're going to realize that if I oxidize something, I release energy. And if I reduce something, that stores energy. And I'm giving you guys that ahead of time, meaning I'm going to come back in like 10 weeks and expect you to remember that. Well, okay, we'll cover it a second time, but you know, I figure if you hear it more than once, it might stick in your head. And the way I really remember this is that I always remember this molecule, and then if I oxidize it, so notice that this little O means oxidize. And so what happens if I oxidize something? I lose bonds to hydrogen, I gain bonds to oxygen. So eventually what happens if I oxidize this all the way is I get carbon dioxide. And if I remember that this is methane, and this is of course carbon dioxide, another name for methane that you guys might be familiar with is natural gas. And so this stores lots of energy. This is very low in energy. And so if I can remember that methane, and see, methane is natural gas, and I know I use natural gas for cooking and stuff, so I know methane's got to have lots of energy around, right? And really if I oxidize it, which in the case of methane is essentially combusting it, then I realize that you know, methane contains energy, and I know that, you know, reduced molecules that have lots of carbon and hydrogen bonds are storing energy. And if I realize that carbon dioxide has almost no energy, and that anything that's combusted makes carbon dioxide because it's lower in energy, and then the excess is reduced or released as the flame, right? Or when we get to the biological chapters, we know that we inhale oxygen, right? We exhale carbon dioxide, right? And so carbon dioxide is a waste product of us metabolizing things. And it's not like we're really doing a combustion reaction internally. It's not like we have a little furnace down in there, but you know, really, you know, if you want to make it a very simplified picture, that's pretty much what's actually happening. So, long story short, we're going to be doing lots of oxidation reduction reactions. One of the things that we'll note is that this is generic for oxidation, so this is a generic symbol. But there's lots of other ways that we can do it. For instance, we might use, where's my little list? Make sure I get them right. Mostly because it's definitely some day of the week. I guess it's Friday. It's a Friday that feels like a Monday, and I want to make sure I have all the pictures right so you guys don't get screwed up. So we'll find that sometimes we see it as potassium permanganate and water, and we simply heat it up. You might see it as chromic acid, Cr2O7, and sulfuric acid mixture. So this is potassium, oops, not two T's, permanganate. Have you guys seen that already? Yeah, so you've already done an oxidation reaction, right? This is chromic acid. We're also going to have what's called the Alkenes reagent, and that's where we add 2 silver ions, and we have to do it in a basic solution with ammonia. And then we also have one we're going to know as Fehlings/Benedict's, in which we have to add 2 copper ions to something, and we do it in sodium hydroxide and water. And so all of these are essentially the same thing. They're all oxidation reactions. What's going to differ, for instance, in each one is what happened in the potassium permanganate reaction to show that it's a positive. It went from being purple to brownish precipitate, right? And so what differs in each of these reactions is what color change you see. And because oxidations can be both mild and strong, meaning there's different levels of it, kind of. Some of them are going to be mild oxidations, some are going to be strong, and so sometimes they'll react with all types of compounds, sometimes they'll only react with a specific subset. And so, for instance, in the chromic acid one, that's a bright reddish color, and it usually turns to some sort of green or blue. Toluene's reagent, that's silver ions, and it makes a mirror, so it makes a shiny substance. And then like Phalings and Benedict's turns from a nice pretty blue color because of the copper to a brick red precipitate. And so the specifics, the potassium permanganate, chromic acid, Toluene's reagent, and Phalings and Benedict's are going to be what we see in chemistry lab. And we'll also write the reactions down in class quite often. And they're important because what they're going to show us is a very specific type of an oxidation reaction that is accompanied by some sort of obvious change. And then when we use the generic arrow, that's when we just write what happens in an oxidation reaction and we don't worry about all the other details. The less than satisfying part, but also kind of nice part about oxidation and reduction reactions is they're terribly complicated. Meaning the reaction mechanisms are hard. A lot of times you have to have an additional molecules around for them to react, like water or oxygen or something like that. And so we're never going to worry about the mechanism. We're simply going to do the reaction. And so it's it's satisfying in that you just have to remember what to do. It's a little less than satisfying because there's no reason why you're doing it to a certain extent. And anyone that wants to, I can go find my notes about how to do some of the oxidation reduction reactions, and maybe I'll show one mechanism up there. But they're not easy. They're ugly. They're like in my other chemistry class, there's an entire chapter on just oxidation reduction reactions and nothing else. And so we're not going to worry about the details. So for this case, though, what we want to look at for an oxidation reaction is that if I take an alkene and I oxidize it, I get a alcohol. And technically I get what's called a diol. So what does the di mean, do you think? Yeah, that means there's two, and we're going to learn that OL simply means OH groups. And really, you can also think about this. This is really just an addition reaction in this case. It's just that what we're really doing is we're saying that I'm going to take, say, an alkene like this. I'm going to oxidize it, and I add an OH group to both sides. So notice that I certainly lost, or well, I didn't really lose bonds to that as much as I gained bonds to oxygen, because we gained that -O bond, right? And so this is why it's labeled an oxidation. And what we're going to see is that oxidation reduction reactions are just one of those broad categories of reactions that occur over and over and over again in chemistry. And they're also very important biologically. A lot of times they're the reaction that gives us the energy from a reaction. So if you're digesting food, that might be the step or the reaction, the single reaction that gives you or extracts the energy from that, from the chemist, from that, as opposed to the 10 or 15 other reactions that might be happening while we're doing this. So for oxidation reduction reactions, I have to be honest, the only way to really remember these is just brute force. Just say, I'm going to add an OH to both sides of the carbon-carbon double bond and be done with it. And then what we'll usually have is we'll also have a special example of that, meaning if we do what's called the Baer test, that's a very specific example of an oxidation. And so in that case, for instance, if I pick a molecule like this, I'm going to react it with KMNO4. I'm going to react it with water. And I get this molecule plus plus MnO2. And then I ran out of room, so I'll add the plus KOH down at the bottom. And the reason we care about this very specific one is potassium permanganate is purple, and manganese dioxide, which is what that is a brown precipitate. And so what we use this test for is basically we test for the presence of double bonds, for the of either carbon-carbon double bonds or carbon-carbon triple bonds. Meaning it's a really quick and easy test to tell whether you have an alkane, an alkene, or an alkyne. And like for instance, when you did the tests, that one took about 30 seconds, right? Meaning you just milliliter of this, a few drops of this, shake it up and look. Now, the bromine test, on the other hand, which is also a good way to tell the difference between carbon-carbon single bonds and double bonds and triple bonds, that reacted pretty quickly also for carbon-carbon double bonds, right? And we saw a disappearance of a color. And so either one of those tests are something that we can use for sort of a diagnostic test to tell the difference between an alkane, an alkene, and an alkyne. So to summarize, what did you guys learn today? What did you learn? Yeah, you really learned addition reactions. And we know that we can add things like Cl2, or I guess we'll keep it generic, X2, H2, HX, and HOH. And that these are symmetric, right? So they generally lead to one product. These are non-symmetrical, and so they lead to two products, and we have to remember Mark's rule. I should also point out that after this I never spell Markovnikov ever again. Not even sure I really got it right, to be honest, but I kind of like the name Markovnikov. Kind of rolls off the tongue. He's a Russian, so it's a good name. So we just call it Mark's rule most of the time. And we also learned that we can do an oxidation, meaning if we see this arrow, and here we think of this as simply adding OHs to both sides. And we learned very specifically that if I have KMnO4 and water, that again I get a diol, plus I have to remember the MnO2 plus the KOH, and I want to remember that one is purple and one is a brown precipitate. And so, I don't know. I mean, it depends on how you're studying for this and how you're thinking about it. We really only learned 2 or 3 different things, or 4, or if you really want to break it down and you say that adding X2, H2, HX, and OH, or water is different, then that's like 4 right there. And then, you know, if we say, well, carbon-carbon double bonds and triple bonds are different, then you've doubled the number of reactions. But if you really try to narrow it down and say, what's the very minimum I need to know, hopefully it's, if I see a double bond or a triple bond, I add things, right? And I have to recognize the special oxidation conditions. And just remember that what that really means is I'm adding OH to both sides of the bond. Taylor.
Does that say did plus MnO2?
Diol is what it's supposed to be. It makes a diol. And how you remember this stuff is kind of up to you guys too. A lot of times I remember one simple example. Like I said, Mark's rule and Zaitsev's rules are very easy to get, you know, mixed up. So I might try to remember Markovnikov's rule as, you know, I know that I can write a reaction like this, and then I have to remember which one is favored, top or bottom. And so that should remind me that it's the hydrogen goes to the carbon with the most hydrogen. So, homework 20C is due on Tuesday. And I really, the extra credit is due Monday. And what I'm going to really stress is that you do some extra practice over the weekend on stuff that you already know to make sure it's in your head. And then realize that your goal, your challenge for next week, which is probably why I won't make the test on Friday necessarily, your challenge is that Chapter 19 was one set of stuff, right? Chapter 20 was one set of stuff. Now you got to merge them together and realize I'm going to be seeing 19 and 20 all mixed up. Now, I don't have any homework assignments on mixing up Chapter 19 and 20. But there is a lot of extra practice on the website if you notice the way I labeled it. There's Chapter 19, Chapter 20, and then I have something that says simply Exam 1, which is Chapter 19 and 20 all mixed up. And so what you really have to focus on doing and thinking about is, how am I going to tell the difference between stuff in Chapter 19 and stuff in 20? What makes me say I'm going to do a substitution, an elimination, or an addition reaction? Or when I'm naming stuff, what reminds me that you need, an ane, an ene, or an ine? You've got to mix it all up when you practice. If you don't mix it all up when you practice, the test is going to be tough. I also have to be honest, like when I was looking at those reaction worksheets, especially even for like just Chapter 19, man, it all starts to look the same, doesn't it? Because you're always adding chlorine or HCl or this or that. So it's tough. Anyway, that's it for me. Let me go ahead and stop our recording. Maybe I'll bang on it real quick.